So, this is one of the main things we derived when we were discussing last, and you might wonder where this V of r came. Alpha p is of course just Tr phi, and the main thing we did here was to, of course, the V phi we simply substituted by square root of gm over r, but this V of r, if you realize, was simply gotten from the accretion rate, which we've written down earlier. This is essentially the mass conservation equation, right? And this was written as minus 2 pi r times rho times Vr times 2h, right? So this is the accretion rate in grams per second, right? And so this simply is saying that you have an accretion disk like so, right, around a central object, and stuff is moving in this way, yeah, with a radial velocity Vr, slowly sinking in. Of course, Vr is much smaller than V phi. It's slowly sinking in, and it's sinking in through this side surface, yeah, the area of which is 2 pi r times 2h. 2h would be this, the height of the disk. So 2 pi r times 2h times rho times Vr gives you grams per second. So that's all this equation is telling you, and this was used in eliminating V sub r, and that's how you get this equation. So this is the azimuthal momentum equation, and that pretty much finishes our discussion of the momentum equation. And the main thing, the reason it's not so much as to show you all the equations and so on and so forth, one of the main reasons we discussed this was to introduce the famous Shakura-Sunyaev parameterization for the r phi component of the viscous stress tensor, and that is this. And this is where the all important viscosity parameter alpha is introduced, and the alpha is always between 0 and 1, and we've discussed what this means, right? Okay, so now we are now ready to discuss the energy equation. Now that we're done with mass conservation, which is essentially this, right? All the three components of the momentum conservation, and now we are ready to discuss the energy equation. And before doing that, though, let us sort of step back briefly to try to understand what we are expecting, right? So when we were looking at the top view of an accretion disk, you remember this is the picture we had. We had a picture where the inner parts of the accretion disk, that's a central object. Maybe I should erase that, and I should put the central object somewhere here. Okay, so the inner parts of the accretion disk are moving faster than the outer parts, right? And the fact that you have this shear kind of motion points to the fact that there are, little rubber bands connecting these layers, opposing the sliding of this layer over this layer. Right? But we also know that viscosity is a dissipative thing. It appears in the momentum equation, yeah, but we also know that viscosity causes energy dissipation. Viscosity and energy dissipation go hand in hand. And why are we interested in energy dissipation? Well, that's the whole point, isn't it? Accretion disks that look like this, they can be accreting, anything can be happening, right? We are not in a position to go to the active galactic nucleus and see what's going on. What we observe are photons, and photons most likely from the accretion disk. Photons. Why are they photons? Because the accretion disk is heated up. Who's heating it? In other words, who's dissipating the energy? The energy is being dissipated due to viscosity. Hence, the importance of the energy equation. Okay? So, because the only way we can observe the accretion disk is via the photons that are being emitted from the accretion disk, very, very indirect of course. So to speak, the process of accretion, in this case we are discussing disk accretion, is enabled by shear viscosity. Hence, and we saw how shear viscosity is parameterized in terms of the alpha parameter, right. So, it is enabled by the shear viscosity, okay, and results in energy dissipation heating of the disk, heating of this disk, of this entire disk here. The viscosity which enables the disk accretion to proceed, that results in heating of the disk, right, and the disk gets heated, its blackbody temperature rises and it emits electromagnetic radiation which enables us to see the accretion disk. So, therefore, let us now try to see what is the rate of dissipation of energy. This is the question that we are trying to address now, okay, and where does this viscosity business come in, right. So, let us now go back. You remember that we were writing Tr phi is equal to alpha p. This is one of the main this is the famous Shakura-Sunyaev parameterization, and by definition this Tr phi is something like eta times dV phi dr, right, because this is the definition of the viscous of this R phi component of the stress tensor, right. So, it's like this, there is a dV phi, this would be the phi direction. So, this would be the phi direction and this would be the r direction, and so there is a r directed gradient of the phi component of the velocity. There is an r directed gradient of the phi component of the velocity, and that is exactly how this is written. So, this is the basic definition and we parameterized it as alpha p, isn't it? And since V phi is taken to be the Keplerian value, right, and the V phi can also be written as r times omega Keplerian, okay. This equality, this equals this can be written as alpha p is equal to 3/2 eta omega Keplerian. Okay, so this is one very interesting thing, and then we also saw that the alpha p, we also saw earlier that the alpha p was equal to rho Vr V phi. You remember this? You remember this from here. This came from the basic momentum equation like this. Where did this come from? This simply came from the phi component of this just simply came from here, right? And this was simplified using this, we simplified it to be this. So, essentially rho Vr V phi is nothing but Tr phi, which in turn is alpha p. So, we are back to this. So, we equate this to this. We equate rho Vr V phi to this guy, right. So, and this helps us get a very interesting result, okay. And again, substituting for the radial velocity in terms of the accretion rate like this, using the accretion rate to get rid of this Vr radial velocity, we get the following very interesting expression, very interesting quality for the viscosity parameter. This is equal to 2/3 m dot over h. Why is this interesting? This is because you see the m dot is global thing. It's essentially the amount of grams per second that the central object is able to swallow, right? And h is the thickness of the accretion disk. These are all global things, and this is being related to the microphysical properties of the accreting matter, which is embodied by eta. Okay, so and if you remember, the dissipation rate, the viscous dissipation rate, if you go back to our discussion of the energy equation, the viscous dissipation rate is given by something like this. In particular, if we write down an expression for d of r, which is given by ergs per second per centimeter squared, okay, this would essentially represent the number of ergs per second per centimeter squared, the energy flux coming out from the face of the accretion disk, which is essentially, what we would observe. Not directly the energy flux that's dissipated due to dissipation, but the energy flux which enables a heating, and therefore the photons that are indirectly a product of this kind of viscous dissipation, right? So this would be given by using an expression that's very analogous to this. This would be 1/2 eta over rho 2 rho h r d omega dr quantity squared, and this omega is essentially omega Keplerian. And if you substitute these rows cancel out, and if you substitute for this omega Keplerian, and if you substitute for this eta using this expression, you get the following nice expression for the number of ergs per second per centimeter squared that's potentially available via viscous dissipation, okay, available to heat the disk, and the heated disk of course radiates, okay, and so that would be essentially d of r is equal to 3 over 8 pi. This is a fairly simple algebra. I urge you to work through this. I've given you all the steps. This is a very nice expression. Nice because it does not depend upon the microphysics. This expression does not depend upon the microphysics of the viscosity at all. Okay, you give me a certain black hole or a certain compact object with this mass, right, which is sucking in matter at a certain rate m dot, and at a particular radius, this is the amount of ergs per second per centimeter squared that is available via viscous dissipation, and this expression is independent of all the microphysics. It's very interesting. Okay, so this is essentially the upshot of the energy equation. Okay, so having now talked about the basics of disk accretion, the basics of quasi-Keplerian disk accretion, let us now move to slightly more detailed topics. And one of the detailed topics is as follows. Many times what happens is, as matter falls in, you see, there is not enough time for, so let's simply talk about an electron proton plasma, a fully ionized hydrogen. Let's neglect the presence of other heavy elements, so only electrons and protons. Let's talk about this, right? Now it turns out that the time scale it takes for electrons and electrons to equilibrate to a Maxwellian distribution via Coulomb collisions, okay, is most of the time it's shorter than the time scale it takes for protons and protons to equilibrate to a Maxwellian distribution, in other words to have a well defined temperature, also via Coulomb collisions, and this in turn is shorter than the time scale it takes for electrons and protons to equilibrate amongst each other via Coulomb collisions. Okay. Now this is something that's universally, that's always true. Okay, this is always true. The reason I'm hinting at this is because sometimes what happens is there is enough time during the accretion process. Remember, the accretion process is one where matter is swept in radially. During the accretion process, there is enough time for electrons and electrons to equilibrate. So there would be a T accretion, right? A T accretion, which is given by some kind of VR over R, right? The radial velocity divided by the local radius at a given. So this would be the time scale at which, over which stuff accretes. Okay, and given this kind of time scale, there might be enough time for the electrons and electrons to equilibrate. In other words, the T accretion is larger than the TEE. So by the time a given parcel of gas moves in, okay, there is enough time for electrons and electrons to equilibrate among themselves via Coulomb collision. So there is a well defined electron temperature. There might be enough time for the protons to equilibrate among each other. Maybe, may not be, that's not always the case. Okay, this is not clear. But definitely there is not enough time for the electrons and protons to equilibrate amongst each other. So the T accretion would be somewhere here. Okay, which is saying that there is enough time for a definite electron temperature to be established. Okay, and if the T accretion is somewhere here, okay, then there is not even enough time for the protons to collide amongst each other and establish a certain temperature equilibrium. But it's not clear whether the T accretion is on this side or this side of the equality. But definitely T accretion is smaller than TEP. In other words, there is not enough time, there is most of the time, there is enough time for electrons among themselves, for protons to equilibrate among themselves, maybe, but not enough time, for E and P to equilibrate. In other words, there can be situations where the VR is such that there is not enough time for the electrons and protons to equilibrate among themselves. There is not enough time for interspecies equilibration. There is enough time for intraspecies equilibration, but not enough time for interspecies equilibration. In such a situation, what happens is the electrons equilibrate to form an electron temperature, and that is typically lower than the temperature attained by the protons. Okay. And if there was enough time for the protons and electrons to equilibrate among themselves, the TP would be the same as TE, but there is not enough time. You see, that's the whole point. There is not enough time for electrons and protons to equilibrate among themselves. Therefore, many times this equality is very severe, and this is what's called the two temperature criterion. Okay, many times this happens. So the plasma that's accreting is not a single temperature plasma. The proton temperatures are typically much higher than the electron temperatures. Now you might ask, why are the proton temperatures typically higher? That's because Viscous dissipation is the primary agent that's responsible for heating the plasma, right? Now viscous dissipation is a momentum based process, okay, and so viscous dissipation essentially, since it's a momentum based process, it appears in the momentum equation. We know this, right? So since viscous dissipation is a momentum based process, what happens is it preferentially gives more energy to the heavier species, which are the protons. Okay, and protons typically are heavier and therefore they radiate much slower, and this is something that you will realize after you after you study radiation processes. Okay, so protons radiate much more slowly as opposed to electrons. So first of all, protons preferentially get the energy. Protons are the ones which are preferentially getting the energy. Electrons are the ones which are not preferentially getting the energy. And to make matters worse, electrons are radiating faster. Okay, so naturally there's a natural, there's always already a tendency by which protons will tend to remain hotter. They're getting energy faster and they're not radiating, they're not giving away energy fast either, so they're keeping it bottled up. Okay, more so than electrons, therefore protons do tend to be hotter than the electrons. What is more, to make matters worse, there is not enough time for the protons and electrons to equilibrate amongst each other before a given parcel of plasma is swept into the black hole. Okay, this time scale is too small. It's somewhere here. So these three things conspire amongst each other to leave the protons much hotter than the electrons. And this is what's called the two temperature criterion. And this essentially limits the m dot. Okay, and this is what it all boils down to. The m dot, the accretion rate, has an upper limit. Now we've already encountered an upper limit on the accretion rate, and that is the Eddington accretion rate. This is yet another upper limit on the accretion rate. Okay, if the accretion rate is any larger than this, then you will always have a two temperature plasma. Okay, so if you're so greedy that you want to accrete stuff really fast, right, then you are bound to end up with a two temperature plasma. And this is important because a two temperature plasma is a collision-less plasma. Okay, when the temperature of the protons is so high, what happens is the mean free path of the protons is much larger. Many times it becomes larger than the disk height. It becomes larger than this, larger than the disk height. And so when the mean free path of the protons is larger than the disk height, there are problems, right? We know that the entire fluid picture breaks down. And so you have to take recourse to not collisions between protons and protons themselves, but collisions between protons and other kinds of scattering centers that could be, maybe turbulent scattering centers or something like that, in order to even meaningfully talk about proton temperature. Okay, and so these are essentially, the point I'm trying to make is that although we have been talking about accretion disk viscosity and how important it is to the entire accretion process, many times it becomes a slightly complicated situation, especially for plasma such as a two temperature plasma, and in situations where the proton temperature is very high, say in excess of about 10 raised to 11 to 10 raised to 12 Kelvin. Okay, and in such situations, the whole concept of accretion disk viscosity becomes considerably more complicated, and our classical descriptions of viscosity no longer hold. But that's a subject that's somewhat advanced, and we won't bother about it. So this pretty much closes our discussion of accretion disks, and soon enough we will move on from this subject, and we will start discussing other things, other astrophysical applications of fluid dynamics, such as supernovae and supernovae shocks and so on and so forth. So that's all for now. Thank you.